Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video today is going to take a look at a lot of stuff. Wow, goodness, right? So, bits, bytewise operations, casting, memory organization, and byte ordering, things you probably never thought about before. So let's start up with something like this here. So many bits, right? So our computers have how many gigabytes of RAM? And what does that mean, right? A gigabyte is a billion bytes, and each one of those bytes is 8 bits. So my goodness, right? Think about a long street, a long avenue of bits that go on, and it feels like it goes on forever. We feel like we have infinite amount of memory, infinite amount of infinite processing, you name it, right? So where do we end? What does it all mean? And so when it comes down to it, the encoding of the values that are sitting on this, sitting in these places is all that matters. Where do I start from? Where do I end? How do I interpret that data? Because there's so many different data formats that I can follow, so it really matters. And so, like, an integer versus a floating point versus a character versus an ASCII character versus a different type of character system, Unicode or whatnot. So every type of system stores that data differently, because you could store it in RAM, you could store it on a register, you could store it on a hard drive, you could store it on a CD-ROM, you could store it in like an optical drive or one of those old tape drives or something like that. There's so many different ways you could store this information. And so generally here, when we're like bistable memory elements are used, bistable so in order to be stable in two different ways, to have what we consider an off condition and an on condition. That matters. And so everything, again, stores information differently, so there needs to be a way to put information onto those devices or onto those things, whatever those things are, and ways to get information off of it. And of course, the real world is never as simple as we think of it. Like I say, we always think in pretty much happy day situations here. The wiring that's involved with all this is noisy and prone to inaccuracy, and nothing is easy as on and off. There's always something in the way. So like for this, like this is voltage. So 0 voltage off is usually considered in some range, and on is usually, I mean, this doesn't have to be, I don't know exactly what I'm staring at here, but you can see 1 volt could be on and 0 volts could be off. And so how do you know if your RAM, or how do you know if this piece of memory is bad? Well, what if maybe I get more than 1? Maybe I get 1.9, or maybe I get 0.6. It's like if everything is expected to be in a certain range and I'm not in that range for a specific value, then yes, this piece of RAM, or this piece of memory might be wrong. So coming back to our idea of representing information, you go, well, not every number value that can be represented as 32-bit integer can be represented as a 32-bit float, and so forth and so on. And just thinking of the data formats. So like 15,213 in decimal is this. However many 15 digits or however many digits we need to represent that. And so, oh my goodness, all these little rules that we have to think of, but everything that can be represented as 32-bit integer can be represented as a 64-bit double, and all these extra little things, right? So it all matters. And so even in binary, it doesn't, there's different ways to represent values. So 15,213 now in decimal, reduced to binary scientific notation, as you'll see in this video, or maybe not this video, but very soon thereafter, you will see how we can take 15,213 and convert it into a floating point equivalent, which will look nothing like the 15,213 that we're staring at right here where my mouse is. And so something like 1.20, how do we represent that in binary? Like most programmers have worked in whole numbers, integer values, but how many programmers, depends on where you've taken your classes, how often do we deal with the fractional? Who came up with the idea of the IEEE 754 standard and so forth? So 1.20 is actually what we call a rational in binary, meaning it doesn't matter how many bits I give you, you'll never be able to represent 1.20 exactly. Think of pi or e. Like, all we can do is approximate it. As long as we're writing digits out, we're just approximating the value, and the more digits we can supply, the closer to the true value we get. But at the end of the day, we're never going to get exactly there. And that applies to so many numbers in binary. Pretty much anything that does not end in a power of 2 on the denominator side for a fractional component, the number is irrational, and there's going to be some error term involved. And that's just the way things go. So coming now around here, so if this is the first time, this is the first time, or of many that we'll be discussing bitwise Boolean algebra. I think we cover that in the Boolean algebra section there. And so remember, there's only 2 states when we're dealing with this kind of stuff. There's an on and an off, a 0 and a 1, a set and a clear. There's so many different ways to represent the 2 pieces of data. And so dealing with this bitwise, that means that when I'm dealing with 2 separate quantities and I'm bitwise anding them together, this isn't like addition or subtraction where things carry or anything like that. We're literally just going down the row and just comparing for equivalent values in, not equivalent, what's the term? Respective elements inside of here. What do you get? 1 and 1, right? So this is a different chart here. 1 and 1 is 1 and everything else is 0. Because again, an and is only true if both are true. So this is true, 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 false, 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 true, false. So on a bitwise manner, one at a time, you get the result. You do the same operation 8 times over and you get the result. Same goes for OR, but again reversed. Because an OR is true if either one or both are true, and it's only false. This is inclusive OR, and it's only false if one of them, or sorry, if none of them are true. And that's the pipe. Like I said, ampersand versus pipe when it comes to the way most languages represent this concept. So this is an OR. Anytime I see a 1, just throw a 1 into the spot, and if I see 2 zeros, then that's the only time that I do this, right? So 0, 0 gets me 0. Everything else has it, except for this one too. 0, 0 has me 0. Everything else has a 1. So coming back to the idea of the mathematical sets, so we can take a look at and say representing 0, 1, 1, 0, 1, 0, 0, 1, starting over here and saying, okay, bit 0 is set, bit 3, bit 5, bit 6, and down here say 0, 2, 4, and 6. So this, again, this eliminates the tediousness of this all. And so, because it's very easy, I do it all the time, where you draw your zeros much bigger than you draw your ones, and then you draw a couple ones, and then you're off by unless you use like a piece of graph paper or something like that. So this is pretty easy, because if I can take these 2 sets and order them together, and them together, and then what do I get? Which values are in both sets? 0 and 6, which means bits 0 and 6, and everything else is unset. And the same with the OR. Bit 0, 2, 3, 4, 5, 6 are set. And so you just fill in the gaps and say, this gets me, this is not a good answer, 0 through 6 like that, but you can convert it very easily, and it's much easier than the alternatives. So here's exclusive OR. So exclusive OR, again, is it's in one or the other, but not both. So exclusively, it's true if it's exclusively one or the other. So in this case, 0 and 6 are in both, so no, but 2, 3, 4, and 5 are in one, but not the other. So those are the 4 values that would XOR, and then you would put those in there. And so the NOT operation to finish the deal is basically used on 1 input, not 2. Everything else needs an A and a B, or however you want to think of it. This just needs 1 input, just an A or an X or whatever. So you can only resolve not A one at a time. And mathematically speaking, this, you have to understand where your limits are, because we're dealing with 8 bits here. So anything from 0 to 7 that's not in the set is the NOT of this. So there isn't a 1, a 2, a 4, or a 7, and that's where this comes from. And in this case, there's no 1, there's no 4, there's no 5, and there's no 7. And then just fill in the gaps. Alright, so in previous videos we spent plenty of time assigned arithmetic, looking into 2's complement. How can I represent a binary number as a positive, and then how could I represent the magnitude of that as a negative value, so -5 and +5 and so forth and so on. So this is one way. Let's say just slap a negative sign on it, right? And we just negate the operation. But the reality is that what you could also do is do this operation. How often do you use the tilde, right? At all, right? And let alone in programming. But we do use it for destructors and a few other things in programming. But if then that's a not operation in C++ and many other languages. So if I take, say, if I take x and I go ahead and I negate the whole thing. So I take all the ones and turn them into zeros, turn all the zeros, turn them into ones. And so what do I get? I get 1, 0, 0, 1, 1, 1, 0, 1 becomes 0, 1, 1, 0, 0, 0, 1, 0. If I add the two things together, I get basically max int. I get 1, 1, 1, 1, 1, 1, 1, 1. And so if you want to think of this from a signed standpoint, that's -1. And if I were to add 1 to this, I'd get an overflow, but it wouldn't matter. I would get 0 at the end of the day. And so the thought process here is, just working out the mathematics of this. If I negate any value, any integer value, and add 1 to it, I should be able to get its additive inverse. It's the negative of that quantity. And so for anything, say the computer scientists in us go, this is, if it works for all but 1 or 2 cases, yeah, let's ship it. But mathematicians, right, and for good reason, are all about proving things work for all values and figuring out why, if they don't work for all values, why, and how can we patch this up, or how do we come up with a better proof so it works for all values. So my question to you, and I'm going to leave this, and you'll see this in plenty of other cases, does this work for all values of x? You should already know the answer to this if you followed other videos, but so I'm not going to answer it. But does this concept of negating x and adding 1 work for everything? And if so, yep, good, that's great. But if it doesn't, which values doesn't it work for, and why doesn't it work for that? That's a big jump for you to make in your understanding if you need to go there right now. Is just look at the ranges of integer values, look at what, signed versus unsigned and things like that, and see if you can come up with that understanding. Okay, so huge difference in C++ and other languages between the single ampersand and the single pipe and the double pipe, and the not, the exclamation point, and the tilde, right? So all of the stuff we were discussing is the single version and an or. That's a bitwise operation. So that's much different than what you see inside of normal if statements when it comes to double ampersand and double pipe. So I would believe in a lot of other languages other than C++, if you forget the second one, you'll get an error of some sort, but I'm not 100% guaranteed. But C++ definitely silently fails, and silently fails miserably for you if you forget that. And everyone occasionally does, because you think you'd hit it twice, or maybe it's a wireless keyboard, maybe it didn't hear the second click or something like that, and occasionally you can have these kind of errors pop up. So you have to watch out. Yeah, so that one missing character, and then this is no joke. Plenty of people have lost plenty of time over the years trying to find one little character, or adding a semicolon accidentally to a for loop, or just stupid little things that everyone's done over the course of their career. So when it comes to Boolean values in C++, a Boolean false is a 0 value. And normally we would say a Boolean value is true false, off or on, which is 1 bit of storage. But a computer has to store that in a full byte of storage, because a byte is the smallest amount of memory that we can take up. So in C++, when a value is not 0, generally speaking, we would love it to be just 1, just to keep it simple. But if it's anything but 0, the value is true. So I could do like if, and I could put 7 in parentheses in C++, and it would work just the same as saying if true. So that's just the way things go. But when you convert into a bool, it'll take that large value and it'll basically say, hey, let's turn this into a 0 or a 1, because the Boolean itself is defined as only having 2 states, a binary state, off or on, but C++ allows for a little bit of a change there. So bit shifting operations, we will see this in a later video. I have plenty of applications of this. So every time I shift over 1 time, basically take a bunch of bits and shift it over, I'm multiplying by 2. I'm multiplying if I'm going to the left, I'm dividing if I'm going to the right. And just think of it from our standpoint of if I had the number 912, and I said do an integer division by 10 in base 10 math, you would get 91, and then if you needed to, the 2 would be the remainder, or something like that. But the quotient of this, I'm sorry, the quotient of this, or the whatever would be 91. And so it's basically just hacking off a digit. So if I shift everything to the right in binary, I'm just hacking off a digit. And so instead of dividing by 2, I'm in binary base 2, I'm dividing by 2 or multiplying by 2. So every so often, this is a fun one too, where students don't realize, because this is usually the cout operator or the cin operator for these kind of bit shifts. But every so often, a student will screw up, and that one took a long time to figure out, because like, what is this thing doing? To realize, because you don't bit shift very often. But for something like this, to say take my x is 3 and take this and bit shift twice. This basically means shift over 2 times, which means multiply by 2 and multiply by 2. And at the end, I'm multiplying by 4, and x will be set to 12. And so the other way around, take 24 and shift it 3 times over. Divide by 2, divide by 2, divide by 2. You're essentially dividing by 8, and I bring myself back, and now I have the value 3. If I take 24 divided by 8, I get 3. And so if you played through the tetracontiplier level of Human Resource Machine, the game that I have for the beginning part of this class, you can see that we can actually take any multiplication and break it up into a series of bit shifts and additions and subtractions. So like in this case, if I wanted to take something and multiply it by 24, it's not necessarily so easy because it's not a power of 2, but I can break it into its component parts and use the distributive rule to handle this, because I can say, okay, I can't multiply by 24 directly, but I can multiply by 32, and then I can subtract off whatever the same value is multiplied by 8, because 32x minus 8x is 24, and here is the C++ code that you would use to do that, so that I could multiply by 32 and subtract off the same value multiplied by 8. So other weird little rules. I always remember the last question of an 8-hour interview at Midway Games when it came to basically all the little intricacies of what happens if you shift too far or not enough and all this stuff. And thank goodness now I would pass that test with flying colors. But you get undefined behavior if you shift a negative number of bits, or if you shift more than, or like basically 32 bits over for a 32-bit integer, or 8 bits over. Because if I'm just adding zeros 8 times over, I'm going to take a value and eventually I turn it into 0, because I added too much. Like on a chalkboard or on a whiteboard, we can just keep adding zeros until we run off the page. But a computer, a register is a register, a variable is a variable. It's not like everything shifts over to make room for the stuff that we're worrying about. All right, it might be news to you. It was kind of one of those things where I didn't really know this until one day. It's like, are you kidding me? The Java language Java, does not have an unsigned data type. Everything in Java is a signed data type. So it's only the older languages like C++ and C and those really, really old languages that have to deal with, well, what if I have a signed number and I have an unsigned number? It'd be really nice nowadays if, for backwards compatibility, get rid of backwards compatibility for the x86 chip and just get rid of all the unsigned arithmetic that can go on and just simplify the entire chip. But so much code runs on that these days that, how much, my goodness, almost every processor feels like out there is an x86 chip. So doing that would be impractical. So we have to watch out. So in high-level languages, what would happen? So whenever we cast from one type to another, there's the possibility of data corruption. So like int to float, or float to double, or double to bool, or like all these weird little things. You could try to do it, but at the end of the day, can you do it? Sometimes the answer is yes, sometimes the answer is no, and sometimes the answer is maybe. And that maybe part is the part that really sucks, because you never know. If you didn't account for that, if that maybe comes up, you have a bug in your code. So we call it implicit versus explicit casting. The static cast operation in C++ is an explicit operation, because you're explicitly saying cast this from type A to type B. And so, but otherwise, sometimes if you pass a variable along, you don't even notice sometimes, right? You pass an int along into a function and it's actually a float on the other end. It implicitly converts it. C++ will try to take that value and basically cast it into a float without specifically, explicitly telling you that that has occurred. And so that's, especially that kind of thing, most newer languages don't allow for that, especially if you're condensing down. But as you're expanding out, it's usually pretty good. So when casting between the two data types, The bit pattern, of course, we're trying to maintain the bit pattern as well as we can, though the value can be now reinterpreted because now it's in a different data format. As much as signed and unsigned doesn't feel like it, but you know better. You did two's complement. You know now that the data representation is different. And so in C++, at least, if there's a signed versus an unsigned variable, the signed values are cast to unsigned. That one does not make any sense to me. I would figure you would reverse it and take the unsigned and convert it to a signed, but I did not devise up the chip or anything with it. And so I actually saw this one time. This popped up in a C++ class, advanced C++ class, where I didn't realize we were mixing signed and unsigned values, and just everything went to hell. And we're all staring at this code, and it turned out it was exactly this problem, that very subtle bug where an assigned value got turned to an unsigned value, and we got the wrong result, and nothing came up correct. And so, depending on the value, if you have an unsigned value that's larger than a signed data type can store, you're going to lose up to a factor of 2. And this is the best part about this, LOL here, is the compiler is totally okay with it. Will not even give you a warning that you're going to completely corrupt the data that's sitting in a variable or sitting in a register. So again, what happens now if I'm expanding? So this is saying, let's say I'm in a character and I want to expand it out into a word. So what happens is, if it's unsigned, the larger space just gets filled with a 0. So we can totally do that, right? Is just add zeros, just pad the thing with zeros and call it a day. Perfectly legitimate. But for signed values, I can't just do that, because if my signed byte was a negative value and I just add zeros, I've turned that negative number into a positive number, because that 0 way at the most significant bit is going to matter now. And then that's going to come up as a positive. So when you're extending out that way, you have to worry about the signed bit. So you'll extend out a 0 if it's positive, just like the unsigned type, but you'll extend out a 1 if you have to for the negative type. And so in either case, you can always expand out into more space in both signed and unsigned types, and the result is exactly the same. The data format's going to be different, of course, because we're changing the format of things, two's complement and all this other stuff. But at the end of the day, the value of the number is going to be left alone. That is not true for truncations. And this is where the maybe comes in. So if I had an int, 32 bits of storage, and I want to take this and I want to condense it down into 8 bits of storage, you're like, well, this is where the maybe comes in. It's like, can I do that? Can I condense this thing down? And yes, if I'm not using the 24 bits that are not part of the byte of my number, yeah, I can take it out, because those are all zeros. I can lose all the zeros. Even if it's a negative number, I can lose the ones. That's perfectly fine. It's just if I'm using more than 8 bits to represent the number and I condense it down, I'm going to get an overflow underflow condition. Something's going to go horribly wrong. Because like even 256 cannot be represented. It would be a 0. 256 is 0 if I took, because it's just cutting off and basically doing a modulus operation on this. 1 with 8 zeros, mod 256. 256 mod 256 is 0. So again, as long as there's no 1 bits in the extra space that you're truncating and cutting off, you'll be totally fine. So that usually happens in almost everything we do on the level of at the educational level. That is definitely not true out in the real world, out in the field, where numbers come in all sorts of shapes and sizes, and we have to be able to account for that. Okay, so we'll see this plenty. Multiplication, binary multiplication. Yes, of course, there's a multiplication and a division operation sitting on your CPU, but those are general use. And you'll see I even have comments in some of my other videos. It's like for multiplication, it's like, just use bit shifting. I'm like, I completely agree with you that bit shifting is always a faster way than just using the general purpose mul and division. However, well, at least for mul. But but on the other hand, we can use this, as we've just discussed. We can worry about the bit shifting stuff if we want to. And the compiler, I have not seen this in practice, but here, I guess it depends on the optimizations you apply to the compiler. And let's just go with the fact that it says the compiler automatically changes everything multiplication into bit shifts if it can speed up the operation. And that's a big if. And it depends on your compiler, it depends on who's smart enough to write it and add the optimizations. and depending on a lot of factors. So don't trust it. Say that as a programmer, it's hard because you want to trust libraries, you want to trust a lot of other people's code up to a point. But when it comes down to it, you're the one who has to go ahead. If you really want this thing to be sped up, you're the one who has to dig in there and make it work. And so for multiplication, just like if I take 9 times 9 and I get 81, a 1-digit number times a 1-digit number got me a 2-digit number. The same thing applies in binary. If I multiply an 8-digit number, I'm sorry, 8-bit number times an 8-bit number, I can get a 16-bit result. 255 times 255 is 65,535. And that can only be stored in 16 bits. So you have to understand that, and that's just part of where multiplication and division is trickier than just addition and subtraction, is that we have to have extra space for that overflow just in case it occurs. We don't see that in C++ and Java, but under the hood, there is a mechanism in place to be able to handle that overflow. And so, arbitrary precision, have you ever used Python? Have you ever just typed in a huge number in Python? It can handle it. It turns that into whatever, it turns it into whatever large number class that the thing has running under the hood. So you can even have, well, maybe not 23 million digits, or maybe, I don't know, I've never tried it out, but you can have arbitrarily huge numbers that can be stored as a data type that you can't simply do in anything else, because under the hood, with assembly language and C, we only deal with 8 bits, 16, 32, and 64. Anything more, we would require some kind of library to make this thing work. And Python is using a library. It's just part of the language. And that's why, how many years, 60, 70 years of advancements in programming and advancements in hardware and software and all this optimization, we're here. That's why Python is like the biggest language in the world, because it just can do so much and it just does it effortlessly. Someone wrote all the code for us so that we can make it effortless. So let's take a look at a simple little snippet of code that can cause a ton of trouble here. So the compiler is more than happy to help me with this and help me to cause this kind of error that I might not notice, or in this case, you would notice this immediately. So what is wrong with this? I have an array of 1,000 integers, so 4,000 bytes of storage in my case, or at least on this architecture. I can do this because this is a const. I'm allowed to do this. So I'm saying, okay, start from size -2, and as long as I is greater than or equal to 0, while I decrement, basically copy data over. So basically just shift everything over 1 to the left, essentially just kind of removing the first element or the front. This is like if I could do a pop front in C++ vectors, which I can't, that's kind of how it would work. Like shift everything over, but what's the problem here, right? Like this is greater than or equal to 0, that's fine. We start size -2, so I don't have to worry about accidentally overstepping my bounds on the high end. But yeah, what happens is unsigned int is basically always going to be greater than or equal to 0. It's unsigned. So this is an infinite loop. So when I get to 0, when I bring this thing down to 0, 0 will be greater than or equal to 0. And then when I go ahead and I subtract it one more time, it'll be -1, but in reality, since it's an unsigned data representation, we're looking at max int. So it's going to try to look at array element 4.29 billion. And I don't know about you, but I have never seen an array that large, and I can almost guarantee you 99.99999% you're going to crash. But when architecture dependent, I could almost guarantee you would be that first time. But again, back in the old days, it might not crash the system. But today, in a modern environment, absolutely it'll crash somewhere along the line. So you're like, well, how can I fix this? Maybe you know the obvious answer, but one of the things that you might think of, especially if you're an experienced C++ programmer, is let's just use size t. And so, size t is just, basically a fancy data type sitting under the hood as part of the standard template library, because, a lot of times these you get warnings, compiler warnings when you're running your code, and you're using data type mismatches and things like that. So you learn, and then once you learn about size t, it's like, let's just jam this in here. Let's use size t everywhere. But when you go and you run through and you kind of backtrack through, or you read the Jasudis book on C++ standard template library, or the Strustrup book, you name it, you find out that under the hood, the size t is the exact same thing as before. It's just a fancy term for an unsigned integer value. And so just by by thinking, oh, this is awesome, yeah, it looks, you look more professional, you look like you know what you're doing, but you're still going to crash it exactly the same as you were before. So it's just a fancy unsigned int. So the best solution, of course, at the end of the day, is use an signed integer value for something like this to make sure that if you're going backwards, that when I go from 0 to -1, the signed value will read it as an actual -1. So that's all I wanted to say about that. So if you're using an array, here's the should, because you should be able to determine how many elements are in that array. You should store it like I did here by having some constant available to you. You should not just hard code the 1,000 in there because now I can use this in multiple places. I don't have to fix up my code when my boss comes in and says, hey, let's make it 2,000 now. Let's make it 4,000 every, or whatever it is it needs to be. I just have to change it in one place rather than worry about all the other places I have to put it. We call that a magic number. And so we try to minimize the magic numbers that we have in our code so that for exactly this reason. The code is more readable too because I know what size means in this context. But if you just were staring at a 998 or a 2,917, you're like, what is that doing here? It doesn't make much sense. But if it was sitting here with a context and a comment, you would know what's up with that situation here. So so for an array, store that thing, and for standard STL containers, vector list, you name it, there is the size function that you can get that information automatically because it's already stored as part of the data structure. Okay, so cool, let's move on. So while I was thinking about that overflow, underflow error, this idea came up to me because this happened back when I was working at a slot machine company. So there was this woman who thought she won $42.9 million. And so you're like, 42.9 million, like what is that going on there? You're like, well, $42.9 million is 4.29 billion pennies. So there was an overflow, there was an underflow on this machine at that specific time, and I don't know why they always use an IGT. They can never figure out why don't you find the real picture of the real machine that broke or whatever. But anyway, 4.29 billion pennies, so there was an underflow. So some subtraction or even an addition or who knows what occurred, and the dollar value flipped into something it wasn't supposed to, because unsigned money on a slot machine is always going to be a positive value, so why not use an unsigned value, right? Except for occasions like this where maybe there's a subtraction and it kicked back around. So anytime you see 42.9 or 21.4 in a mistake when it comes to a computer, you kind of you can jump right to the fact that oopsie, there was just a very small overflow or underflow error. So I just wanted to show this to you and just say that this definitely hurts the reputation of the company. This hurts the reputation of the programmers because that's a big deal to make it out into the world. There's a lot of testing that goes into slot machines, so even after all the months and months and months and months of testing that went on, this still went through out into the world. And just to say, things like this happen all the time, but this was the only mistake I've seen in the last 10 years, or at least in the little bit I spent looking up trying to find this kind of mistake. Okay, so the final big discussion of this lecture today is going to be about memory organization. So what is memory? What is RAM, right? Computer memory is not how we visualize it. We visualize it as one completely long street of bytes, and every byte has its own memory address, basically just like you walk down any street and every house or every building generally has a number associated with it to help everybody along to figure out where everything is, and it's the same kind of deal. And so, but it's much more unclear, right? Because if you've ever put your own computer together, you're popping chips in. It's not linear in any stretch of the imagination, and only a few people know actually how this all works under the hood, but we can still visualize it the same exact way. And so it's an array. What is RAM? Just an index of bytes. It's an array of bytes sitting that I can just access. And the only thing that complicates matters is that the operating system kind of controls this thing and make sure that we can only use certain parts of it at certain times when we ask for it. Because back in the old days, you could just go in and you could just go right into memory and do whatever you wanted, wherever you wanted to do it, because it was your computer. There was no security like there is with Windows and Linux and all that nowadays. And so, but what is a memory address, or, how do I access a memory address, but with a pointer, because it's just a variable that's looking at a specific memory address. So that's all a pointer is. I mean, and I know pointers screw up everybody, me included, going through this, learning how this all works out. But when you completely understand that a pointer is just looking at a memory address sitting in this array of bytes, and you can do anything you want with it once you can get there, it opens up your eyes to pretty much all of how memory is organized and how computer programming works. And so, coming back to this idea here that every program, when you run, gets the permission from the operating system, and the operating system gives you a specific chunk of memory, and you're free to go in there and, it's your walled garden is what the term is for this sort of thing. I can go in there and I can do whatever I want, and I can screw things up inside of there, but I'm not going to get an operating system error. But once I step outside of that and I start jamming stuff outside of that, if I hit an electrical line or something, well, that would be bad, just like in real life, right? If you went outside of somewhere you're not supposed to start digging, it's the same kind of deal where you're going to go into somewhere you don't belong, and the operating system is going to shut you down real fast. So that's kind of the idea, the starting idea of this. And so again, 32-bit mode, which was up until however many years ago, I remember it must have been at least the last 10 years, because I remember it changing over while I was at COD here, since I started teaching, was that I could only access up to 4 gigabytes of memory. And just coming back to the last talk, 4.29 billion, because that's the number that can be held in a 32-bit integer. So that's how much memory you could have. And then we got over that hurdle by moving into the 64-bit realm when it came to all this stuff. Oh, here is it: 16 exabytes of data, 18 billion gigabytes of memory. Because that's what a 64-bit addressing mode can hold. 64 bits can store 18 exabytes. And again, we laugh at this, but maybe one day we'll have to fix that. Maybe 50 to 100 years in the future, you'll have hundreds of exabytes of RAM. Who the hell knows? I mean, who knows what's going to be in the future, right? Like, I had a 500 megabyte hard drive in my computer when I was in high school, and that was like the coolest thing ever. And now that's nothing, right? So same deal kind of applies to us here. But we still need to supply support for older data formats. And so we'll maybe one day, if we ever move up to 128-bit computing and all this, maybe 32-bit will fall away. But 16-bit is starting to fall away now as we're moving into a higher, into the 64-bit era. And it's getting harder and harder to emulate and figure out, or maybe not emulate, but at least to virtualize and get going with a 16-bit environment. Okay, so memory organization here. So everything we're going to discuss here only applies when I'm dealing with a data structure that's more than 1 byte of storage. And so, like for a character of data, 8 bits, 1 byte of storage, I just put that information into that byte, I'm good to go. But for anything larger, I have to put that information in a string of bytes, series of bytes, byte 1, byte 2, byte 3, byte 4. And what might surprise you is that there are 2 competing ways of putting data into those 4 spots. That just sucks. But that's what the whole idea here of Endianness is, and we're going to discuss that in a couple minutes here. But notice, but just to say this right now, a 32-bit word, an integer value, needs to be stored in 4 spaces. A 64-bit word needs to be stored over 8 spaces, because it's 8 bytes of storage, and so forth and so on, depending on what's going on. So, and it's always a contiguous block. One data structure is always stored as a contiguous block. Maybe not like a double-ended queue or some weird data structures, but the elements themselves, ints and floats and characters and shorts and even objects, are always stored in one clump, whatever size is needed, and then you move over that many bytes to get to the next clump of whatever it is that you're dealing with. So now here, coming back, so another question you have to ask yourself as you're going through this is, what is my architecture? And so none of this stuff even shows the 16-bit era that I was going through, because 1994 was when 16-bit and 32-bit were starting to kind of commingle, and now things have changed so much in the last 10 years or so. But now you notice the sizes of the data types, it's malleable. completely depends on the environment you're working in. And in this case, this is C++, this kind of stuff here. C# has completely different requirements. Other languages have completely different requirements for these kind of things. And so this is like the biggest statement I'll say, like for right now, for you guys studying this course, is we are going to be sitting here in the typical 32-bit environment. So when it comes to the data types that we're discussing, let's say this again, this is very important. This is the column that matters to you in this course. We're going to be using characters, which are 1 byte of storage. A short is 2. An int is 4. Notice that the long is actually 4 on a 32-bit environment because there's no guarantee that you have a 64-bit register in a 32-bit environment. And so once we move up to the 64-bit environment, yes, we do. But if I want to access, and since we are using 32-bit mode, but every computer that exists in the last however many years is now 64-bit architecture, that we use long. I know it's funny, but that's exactly what they ran out of ideas for naming these things. But long is actually 8 bytes of storage. And that's a quad word, if you want to think of it. And when we deal with this in our assembly language discussions, character is going to be a byte, short is going to be a word, int is going to be a double word, and long is going to be a quad word. So just remember that, write that down, and just store that somewhere, keep that off to the side, and come back in the next lecture or two and beyond when we start actually dealing with these data types. But notice float and double will always stay the same because that is a completely different standard from previous lectures. The IEEE 754 standard. Float is always 4 bytes, double is always 8 bytes, and there's actually a long double sitting on the processor that we can't deal with in 32-bit mode or even typical 64-bit mode, and it's usually 10 bytes. It's a little bit more extended than even the double data type. That's why it's long double. And so a pointer, you're like, a pointer is a pointer is a pointer. A lot of students get this wrong, and I would say, me too. Like, I was just flipping around, what the heck is this addressing? What is this pointer idea? The pointer is always the size of the architecture, or basically I'm dealing with 32-bit mode architecture here, so that's basically address mode. So that's 4 bytes of storage. A 64-bit addressing mode requires 8 bytes of storage. So just that's how things go. So a pointer to a character, or a pointer to a short, or a pointer to a werewolf object, or who knows what in a video game, it's always going to be 4 bytes of storage because it's basically where in this contiguous block of memory known as my RAM is the data being stored. And that's always going to be matched up with the architecture. So a pointer is always going to be 32 bits, or in our case, a double word when we're talking about x86 assembly language. So I discussed earlier there are 2 competing ways that we can order bytes inside of our memory when we're dealing with a data structure that's larger than 1 byte of storage. So putting an integer, you would just think, wouldn't you just think, you're like, just put it in the order in which it applies, and just put the first byte first, and the second byte second, and the third byte third, and the fourth byte fourth, and you go, that makes total sense to me, except for the fact that our x86 architecture does not obey those rules because God knows why. So, so there's 2 competing ways: Big Endian versus Little Endian, and it's easier just to show than to describe because Big Endian means the least significant byte has the highest memory address, and Little Endian means the least significant byte has the lowest memory address. So we are living in a Little Endian world on our processor, and most modern processors that the mainstream people use. There are, definitely other processors that reverse back and use what I feel is the more correct way of doing things. But most times, like starting out is a little bit of it gets a little weird, and you only do this occasionally, but you screw up, your brain gets jiggled a few times because of the way data is being manipulated and being reversed and reversed back and all sorts of stuff on the CPU. So Little Endian is what we're dealing with. And so if I was dealing with this number in hex, this is 0, 1, 2, 3, 4, 5, 6, 7 hex, 32-bit quantity. And I'm saying, let's put this value into RAM, into the 4 bytes of storage, using the 2 different methods. And so let's just say this is memory address 100, wherever, this is where it's going to go. And you're like, well, what would the byte values be in these spots? And you can go, oh, there we go. This is what Big Endian order, this is the way you would expect it to be. you would expect it to be 0, 1, 2, 3, 4, 5, 6, 7, you know, basically left to right as you read it, as you write it out, as we've been doing as long as we could read and write. But the fact is, again, Little Endian order, the one that we care about, is the exact reverse. You take the bytes, not the bits. That would be crazy if you did the bits completely mirror imaged. But you take each individual byte and you start from the back. So 6, 7, 4, 5, 2, 3, 0, 1. Just think of it crisscrossed. And that's how Little Endian order. That's the way the bytes are stored in memory. Okay, so let's take a look at a few other values here. So another integer value, 15,213, which is 3b6d in hex. And so big Endian order, the way we would expect it to be put into memory would be 0, 0, 0, 0, because we have to front fill with zeros to make this a 32-bit quantity, then 3b, 6d. But again, the reverse of this, the mirror image of the bytes, is what happens when we move over to our Little Endian order, 6d, 3b, 0, 0, 0, 0. So then negative 15,213 gets the same kind of deal, where you're like, okay, it would be C493, and since it's a negative, this value is a C, which is 8 or above, so that screams out negative to me, so I would have to front fill with F's. And so FF, FF to keep this thing negative, C493, and so the bytes again get reversed order to way into how we would do things here on our Little Endian system. Oops, look at all those linkages. So long, long. So this is again like, long versus long versus whatever. Like, gosh, all these different data structures, and it depends on the system, right? So, some long longs are still 32 bits of storage, and some are 64. So it all depends on how your compiler works, how your architecture works. So many little things here. But again, if I'm dealing with this 0, 0, 3b, 6d in big Endian order, that sometimes as we move over into different systems, we have to worry about the Little Endian order. So, and again, it's a big deal, but at the end of the day, we only have to worry about this in a few cases, and only when we're dealing with individual bytes of memory. But the CPU can handle this automatically for us. So at the end of the day, who cares how it's architected? Just say it that way. Because most times we don't have to worry. It could be in a completely different order as long as we don't care. As long as it works, we can black box it, right? So we can say, as long as it works, we're good to go. All these little linkages here. Okay, so a little bit more thing here. So let's see, how are pointers represented? So it's coming back again. It's the same kind of idea. So it depends on your architecture. If you're in a 16-bit architecture or a 32-bit architecture or 64 or who knows what. And so, let's see, many compilers generate different variable addresses every time the program is run, because pointers are, basically pointing to a memory address where another variable or where the real data is stored. And so when a program runs, and the operating system is running and basically giving you a walled garden for your program, every time you run your program, it can potentially, and it most likely will, give you a different splotch of memory to work with. And so the pointer itself will not be hard-coded. It'll be more like soft-coded, because it's like it's usually an offset to something, or it's basically there's a lot of work that goes into figuring out exactly where that pointer is, because everything is always just changing around, because it's like a ebbing and flowing sea of memory, and what is being used and what is not, and all of this kind of stuff. It's just amazing how it all works. So just so you understand that. So just remember, and again, the Endian order matters again, because what is a pointer variable? It's still a variable. So if it's a 32-bit storage or 64-bit storage, depending on your Little Endian or Big Endian architecture, the value is going to be stored using that methodology. And so, like I said, coming back to how strings and character arrays are stored, this breaks everything we were talking about previously, because when you work it down to its elemental level, at least when we're talking about the ASCII code, the ASCII chart, every byte is one, or every character is 1 byte of storage. And because that is the case, we don't ever have to flip the bytes. And so notice for both Little Endian and Big Endian systems here, the byte order, everything is identical, including the null terminating character. And it's one of those things, if this is actually 6 bytes of storage. Even though there's 5 bytes stored here, we need that 6th byte for that 0. And if you fire up Visual Studio and go into C++ and create a string, like a 3-character string, and mouse over the thing, and it will show you that it's a 4-character array. That 0, the programming language, the compiler, will throw the 0 on for us. But again, in assembly language, we don't have that benefit for us here. So again, coming back here, every character is, at least in ASCII, is 1 character at a time, and it's the same for Little Endian and Big Endian. If we were dealing with like different data, different types of characters, like anything Unicode, right, UTF and all these other kind of data structures, or I'm sorry, these kind of different, what's the term for it? The different kind of encoding mechanisms, then all bets would be off, especially if we're dealing with larger than 1 byte of storage. We're right back to where we were, to flipping all the bytes, or not flipping, depending on the architecture. Okay, so I think this is the last slide then. So how do I prove this? Run this code. Take this C++, or this is a C program. Take this C program, copy paste it into your Visual Studio or whatever, run it, and try, if you have, nobody really has access, find a computer that, compile this on a computer that has the other Endian system, and you will see what, Little Endian versus Big Endian. And I guarantee you, on our systems, the one I'm going to be using, the one you're going to be using, most likely here, I can guarantee it, it will be Little Endian, so you'll get the byte order in the Little Endian order. And so this is just, you can tell it's straight P because it's using printf and all sorts of crazy stuff. So it just, it doesn't need to be fancy. It doesn't need to be a C++ program just to get across what you're trying to do. All right, so a lot of stuff going on in this video. So the Little Endian versus Big Endian order, again, is kind of a big deal. There's so many little topics that go into this kind of stuff that compiler designers and developers just kind of remove from us, right? All these things, my goodness, right? Compilers, I can't imagine writing a compiler. I wrote a recognizer once. I never wrote a compiler, especially for something that has to work for millions of people and work perfectly well for millions of people. But anyway, I digress again. So if I said anything wrong, if you have any questions, please send me an email at swardb@cod.edu. I'll get back to you as soon as I can. But again, don't sit on your questions. These things just bubble up and these things start rolling. And if you don't understand something now, it's going to come back, especially the Endianness, in a week or two or whatever. It's going to bite you in the butt because something's not going to work right when you're writing a program. And actually it is right, but you didn't interpret it as correct, and so forth and so on. And you don't want to sit there for 6 hours for something that was right all along. That is like the worst feeling in the world. So again, don't sit on your questions. Please get back to me as soon as you can. And we'll see you in the next video. Thank you, everybody. Have a good day.